All right, so let's get started with today's lecture here. So 5.3, Fundamental Theorem of Calculus, actually has two parts, part 1 and part 2. So how this is going to go is I'm going to go over part 1. I'll go over some properties that we use for finding antiderivatives. And then I'm going to go over part 2, and we're going to calculate definite integrals. You already have an idea of doing this. Let me go back to the previous section here. I'll show you what I'm talking about. So with this previous section here, this is a definite integral because we know that we are starting, let's say, at x equals 0 for region 1, and we are ending at x equals 4 for region 2. So that is a definite integral. There are other things called indefinite integrals, which I'll go over examples of that in a second. Not in a second, I'm sorry, I'm lying. A little bit later on in this lecture. But just know that everything that we've built up to is basically preparing us for this right here, which is just saying that the derivative of the area function is equal to the derivative of the antiderivative from a to x of some function of f of t dt, which is approximately, or which equals, I don't want to say approximately, that's a bad word, which equals the function that you're looking for. In other words, derivatives, and then you have this integral. They are inverse relations of each other. Meaning, if you had, let's say, the integral of x, well, we'll just say x dx, okay? Now, I'm just going to tell you what this answer is. This is an indefinite integral. So this is indefinite. And the answer to this is x squared over 2 plus some arbitrary constant. I will explain what that arbitrary constant thing means later, okay? But the idea is, if you take the antiderivative of x dx, you get this function right here, f of x equals, let me write it underneath, f of x equals x squared over 2 plus some constant c. If I were to take the derivative of this, notice that the derivative would be x, and the derivative of a constant is 0. So I get f prime of x equals x, which is exactly what we started with here. So that is what this fundamental theorem of calculus part 1 is saying. It's saying if you have an area function, and we're going to call this area function the integral from a to x of f of t dt, then its derivative is going to equal the original function that you would have started with. Okay? So let me show you how we actually kind of prove this. So let's say, for example, we have a continuous function. So assume a function f is continuous. On the closed interval from a to b. Then, and I'm going to do this in pictures. So, oh, that's horrible looking. There we go. That looks good. So, right here is a, here is x. And give me a second here. I'm going to make this x plus h. In other words, it's going to be x plus a little bit more. So if I wanted to find this area underneath the curve here, this entire area is going to be the area of a plus h. Now, in a second picture, same function. This area right here is just the area between a and x. Now, that would be the area of ax. So what we know is, if I just wanted to find this little piece right here, okay, which is kind of small, all right, it It almost looks like a rectangle, but if I just wanted to find that little piece, then what I would need to do is take the area of x plus h and subtract away the area of a of x, and that's going to be approximately h times the height of my function, which is f of x. So hopefully you can see how this works. So I'm going to go over just one more time. If our goal is to find that little piece of area right there, that little rectangle, then, and I'm going to use a different color here so you can see what I'm doing. So I'm going to use black. Then what I need to do is find the area of the entire region and then subtract away the area that I don't want. And that will give me the area of this little piece that's left over. All right, now note that as long as h is greater than 0, a of x plus h is the net area of the region whose base is the interval from a to x plus h. And a of x is the net region whose base is the interval from a to x. Now, if I were to set this up, this should start to look a little bit familiar. So watch what I write here. So I know this is going to give me the net area, which is approximately equal to h times, h times f of x. So in the picture above, let me label this for us. This distance right here is going to be h, and then the height is going to be the function itself, okay, f of x, or in this case, you could just call it f. Now, let me get my red marker out here. There we go. So now I kind of have an approximation equation here. Now, remember, if you do something to one side of the equation, you must do it to the other. So what I'm going to do is just divide both sides by h. And notice by doing that, I get a of x plus h minus a of x all over h is approximately equal to f of x. Now, if you think about this, this should look very familiar to us. So this is almost the definition of a derivative. This is almost the definition of a derivative here. So remember, back up in here, let me zoom out here a little bit. Our goal was to find the area of that little region. What if I let h, I'm going to draw this arrow. What if I let that step size, sorry, I wrote the wrong one, approach 0? In other words, I'm going to let that get infinitesimally small. I'm going to let that width of my rectangle just get smaller and smaller and smaller and smaller. Well, what we say is we're going to take the limit as h goes to 0 and remember, I got to do it to both sides. All right. So, excuse me. So if I let the limit as h goes to 0, what's happening here is that rectangle that we're drawing right here, this rectangle right here is getting smaller as h goes to 0. That width is getting smaller and smaller and smaller and smaller and smaller. on the left-hand side, this is your definition of a derivative. And on the right-hand side, this, although it's approximating, will turn into the function itself, because now what you're doing is you're letting that rectangle get smaller and smaller and smaller. So now you're just approximating it. And this is indeed, wish I could spell today, the derivative is approximately the function that we're looking for, because a of x is equal to the integral from a to x of f of t dt. All right? And that leads us into the very first part of the fundamental theorem of calculus, which says, sorry, I'm doing some editing here, which says that the derivative of the area function is equal to the derivative of the antiderivative from a to the x f of t dt, which will give you the original function itself. An easy way for me to think about this, if you have velocity and you integrate the velocity, that gives you displacement, okay? If you have acceleration and you integrate that, you get velocity, which follows that. Now, this is going to look weird, but it is 100% proper to write it this way. If you integrate 2 times, so we call that a double integral. You will learn that in Calc 3. You'll learn about double and triple integrals. So if you have the double integral of acceleration, you can go all the way back to displacement and so forth. Okay? So now I want to go back into section 5. I think it's 5.2 or 5.2, and it deals with properties of integrals. So the reason why I didn't show you the properties of integrals back in 5.2 is because they go over them again here, and now you can actually see how these properties work. So here's our properties right here. So if we have two different functions of x, we can actually combine them. The idea here is this. For the first property, the integral from a to a of f of x dx equals 0, and that's by definition. So the easy way to think about this is, if you have a function, let me draw it a little bit bigger. I'll just erase it. So let's say we have this function that looks like this, and you're integrating from a to a. You're not moving left or right at all. And a line, which you've just created because you're integrating from a to a line has no area. So the area underneath the curve at a line is 0. Remember, a line is nothing more than just a bunch of it's just a bunch of points that are just connected. It's an infinite amount of points from one spot to another spot, or from A to B or whatever. So the integral from A to A is equal to 0. Now the second integral says this. It says the integral from b to a of f of x is equal to the negative integral from a to b. So if you're looking at this, now hopefully you're watching the video right here, because I want you to see how I'm going to shade this. So the integral from b to a of f of x. Oh, you know what? I'm going to do it this way. I don't know why your book wrote it like this. I think it's kind of dumb. But it's their book and they wrote it. So the integral from a to b of f of x dx. What that means is that we're adding the area from left to right. Okay? So we are adding the area from left to right. All right? On the flip side, what property 2 says is that if you wanted to go the opposite way, so if you wanted the integral from B to A, what you're going to have to do is negate. You're going to negate it, which means you're going from B to A. So you're just going in the opposite direction. So that means you're going from right to left. I understand why they wrote it the way they did, but I think they're just confusing people by writing it that way. All right? So, excuse me, you're going to have to use that sometimes, especially when like every single problem is different. Like I wish I could just say, oh, this is what you do every single time. That's not the case. All right? What you're going to have to do is sit down and think about, okay, what's the best way to approximate this area? 99% of the time, you're integrating from A to B of f of x dx. So you're just going to integrate from left to right. It's very rare that you're ever going to do the opposite direction. Although I'm going to do an example that shows you how to do it from in the opposite direction. All right. Step 3 is just if you're adding two different functions, you can separate the integral. All right, which means you could distribute it. Property 4 says you could take a constant and move it out front. Huge. We use that all the time. So if you have a constant times a function, you could pull the constant out front. Let me give you an example of that. Okay, let me give you an example of that. I'm just going to erase this real fast. All right. So you don't have to know how to integrate this one yet. Actually, let me put an X there. There you go. You could take this constant and move it out front. So now your problem is going to look like this before you do any work. Okay, before you do any work, that's what it's going to look like. Okay? So you can move a constant out front. Property 5 says you can separate the intervals if you wanted to. Now, that is really important if you're looking at a problem. Let's say something like this. The integral from -1 to 1 of, let's go with 1 over x. No, that one's not a good one. Here's a better one. If we want to find the integral from -1 to 2 of 6x times x plus 1 times x minus 2 dx. Now, what's going to happen here is, and let me show you what this looks like. Let me get out Desmos real quick. All right, so when we look at this function graph, okay, so that's going to be 6x times x plus 1 times x minus 2. All right, notice that I'm just going to clean this up a little bit here. But you could see hopefully what's happening by now. So let's do 3, and then my y-axis will go -10 to 10. Get rid of those minor lines. All right, so hopefully now you could see what's happening here. Is if I were to find the area underneath this curve, you know what? Let me just bring this into our notes, because then I can just fill it in. All right. Beautiful. So if I wanted to find this area right here from -1 all the way up to 2, notice I have area underneath this curve from here, from -1 to 0, and then from 0 to 2. So if I wanted to find the net area, which is our definite integral, then I would just go from -2 to 1 of my function dx. If I just wanted to find the area, meaning the area of region 1 and region 2, well then, and I'm going to call this total area. Well, what I would have to do is break up the interval from -1 to 0 of f of x dx, and then add the second interval from 0 to 2 of f of x dx. So notice I had to separate the intervals there. That's what property 4 is telling us. It's saying if you wanted to, you can, if you want to find the total area, not just net area, if you want to find the total area from A to B, you can separate this in the regions if you have a function that goes above and below the x-axis. Okay? And then property 6 deals with the absolute value of functions. So with that, you're going to have to just sum up the areas of the regions, which means you have to apply property 5. Remember, the definition of the absolute value is a piecewise defined function that says the absolute value of x is x if x is greater than or equal to 0, or negative x if x is less than 0. So if you wanted to find the area between points A and B, what you're going to have to do is separate this from A to 0 of the absolute value of x dx, and then add it from 0 to B of the absolute value of x dx. Okay? So those are the properties. The most important properties, honestly, the most important ones are going to be 3, 4, and 5. Those are the most important. 1 and 2, you don't really see too much. 6 is special. Put a star next to it because it deals with the absolute value. 99% of the time, you're going to be using 3, 4, and 5. Okay, now, before we go any further, because there is another theorem, I want us to start understanding how to apply the different rules that we have. So, let me change my marker here to black. So, remember with derivatives, we had something called the power rule. And the power rule for derivatives just said that if you had a function of x raised to an exponent, that is equivalent to, if you want to take the derivative, you pull the exponent out front, and then you subtract the exponent itself from 1. So n times x to the n minus 1. An example of that would be x to the 5th power. We know that would be 5x to the 4th. Now with integrals, or the antiderivative, okay, it also has its own little power rule. So let me show you what that looks like. So the integral of x raised to some power times dx is going to equal x raised to the p plus 1 all divided by p plus 1 power plus this arbitrary constant right here. Okay, that's just a constant. Okay? Now, I will come back to this constant in a second. What I want to do is let's just go ahead and do an example. And I think you know what the example I'm going to use is. We're going to do the integral of 5x to the 4th dx, which is what we just found on the left-hand side. So according to our properties, I have a constant. I could pull one out front. So this turns into 5 times the integral of x to the 4th dx. Now I'm going to go ahead and apply this power rule. And I'm going to get 5 out front times. So now I take that power, which is a 4, and I add 1 to it. And then I divide by the same exact number. So it's 5 times x to the 5th over 5 plus some arbitrary constant c. Okay? And if I simplify, 5 times x to the 5th over 5 equals x to the 4th plus c. I'm sorry, x to the 5th plus c. Okay? Now, this plus c thing, here's what's happening, okay? Anytime you take you take an integral of something, all right? And notice I am missing these limits of integration, which I went over in a previous in last week's video. They're called limits of integration, the lower limit and the upper limit, okay? So since I'm missing these, we call this an indefinite integral. And the reason why we call it indefinite is because we don't know where we're starting or where we're ending in terms of finding the area. Now, this plus c means that there are a family of solutions for this problem. In other words, if you think about this, I can have all these different solutions for this problem right here. X to the fifth plus 1, x to the fifth plus 2, x to the fifth minus pi. They're all different solutions or possible solutions. We'll call them possible solutions. Okay? And the reason being is if you recall, the derivative and the integral, or the derivative and the antiderivative, they're inverse properties of each other. So if I were to take the derivative of each one of these different possible solutions, no matter what I do, I'm still going to get 5x to the fourth for a derivative. So we call when we take the antiderivative of an indefinite integral, we don't know what solution we're talking about. So we add this plus c, which is just some constant that we don't know what it is. Okay? An easy way to check yourself is just to take the derivative, and you should get what you originally started with. Okay? Now we can go ahead and start talking about the fundamental theorem of calculus part 2. So the only rule that you really need to know right now is just this power rule, which we're going to use a lot. Okay? We'll go over some other rules when we get there. All right, so our fundamental theorem of calculus. Oh, sorry, I wanted part 1. Hold on. I gotta erase this, put part 2 in there. All right, and we're back. So the fundamental theorem of calculus part 2. What this says is if you have a definite integral from a to b, then what you can do is find the antiderivative of f of x and then evaluate at each one of the endpoints. And that's what the fundamental theorem of calculus part 2 says. So I think it's just best if we just start with a bunch of examples here. So the first example I want to look at here is let's find the integral from 0 to 1 of x squared minus 5x plus 6 dx. Okay? So the first thing that we're going to want to do is find the antiderivative. So the antiderivative is going to be, so let me just rewrite this real quick. Is going to be, now I need to apply the power rule for each one of these, okay? So the power rule for x squared is going to be x to the third over 3. Remember, you add 1 to the exponent and divide by that. Minus 5x to the, well, since this is x to the first, that's going to be 2 over 2. Or I said 2 over 2. What I meant was x to the second power over 2. Plus, now, the integral of a constant equals that constant times x. So let me show you what that means in a second. It's a little bit different, all right? Because what I'm about to write really isn't going to make sense, but it's a good way to think about it. This 6 is really 6x to the 0, okay? So what you're doing here is you're adding 1 to this, and then you're dividing it by 0 plus 1, and that's how we get 6x to the first, okay? So I hope that makes sense. It's an easy way to think about it. So right here is our antiderivative. Now, what we're going to do, and you're going to see this notation a lot, is we're going to evaluate this between 0 and 1. So we draw that line and we put 0 and 1. Now, visually, here's what's happening. I went ahead and graphed this in Desmos. And what I want to know is, what is the area underneath this curve from 0 to 1? And we want to find all of this area right here that I have shaded. Okay? So, like I said, to do that, you find the antiderivative, and then we're going to evaluate this between 0 and 1. So, the 1, we call that, and this is just a little bit of a review, we call this the upper limit. 0 is going to be our lower limit. And according to the Fundamental Theorem of Calculus Part 2, so let me zoom out. This is going to be x cubed over 3 minus 5x squared over 2 plus 6x, where x equals 1, minus x cubed over 3 minus 5x squared over 2 plus 6x, evaluated when x equals 0. So this is going to be your f of b minus f of a. That's what the second part of this fundamental theorem of calculus tells us. It says if you got a definite integral and you found the antiderivative, you can go ahead and substitute in those limits and tell me exactly what that area is underneath that curve. So for us, this is just going to be 1/3 minus 5 over 2 plus 6, all minus 0. See, what I did is I went into my function. Wherever I saw an x, I substituted with a 1. So that's how I got 1/3 minus 5 over 2 plus 6. And then the lower limit 0, so this entire thing just goes to 0. So this entire thing goes to 0. Lastly, when you do the math, you're going to get 23 over 6 as the area underneath this curve. So this area is 23 over 6 square units, if you want to call it that. What I'm really just concerned with is just give me the number. Just 23 over 6. Okay? So there's our first example. What I'm going to do from here now is I'm going to just speed up a little bit. Okay? All right, so here's our next interval. Integral, not interval. So evaluate. The following integral and sketch the graph of the integrand and shade the region. That you want to find. All right, so here's our integral. So it's the integral from -6 to 1 of x squared plus 5x minus 6 dx. All right. So I think the first thing we need to do is just let's go ahead and graph it and let's see what region we want. Now remember, we're going from -6 to 1. So let's go back to Desmos here. And this is going to be x squared plus 5x minus 6. Let me zoom out here a little bit. And we're going from -6 to 1. Okay. So give me 1 second. I'm going to copy and paste this into our notes. let me do that again. Because what I want to do is I want to get that number 1. There we go. I think it looks a lot better. All right, so here's our sketch graph. It's a little bit better than sketched. But notice we're going from -6 to 1. And there's the area right there. So hopefully, when you're looking at this, you're thinking, okay, well, my area better be a negative number because I'm below the x-axis. Like the total part of this region is always below the x-axis. So my area should be a negative number. So for each one of these, we're going to have to apply the power rule. So x squared, the integral of x squared, it's going to be x to the third over 3 plus 5x squared over 2 minus 6x. And we're going to evaluate this between -6 and 1. All right. So I'm going to write it underneath here, because I'm going to write everything out now so you can see it. And this is what I meant by I'm just going to speed things up here a little bit. So this is going to equal 1/3 plus 5 over 2 minus sorry, I wanted to write that a little cleaner, that's all. Minus 6 minus, now this, remember, this is my upper limit. Now my lower limit is going to be -6 to the third over 3 plus 5 times -6 to the second over 2 minus 6 times -6. And this is my lower limit. So I need to just simplify the upper limit, simplify the lower limit, and just subtract those two quantities. All right, so when you do this, the upper limit should simplify down into -19 over 6. And then the upper limit, give me 1 second, I'm just going to use my calculator here. So the lower limit should turn out to be 54. And then when you subtract -19 over 6 minus 54, you're going to get -343 over 6. Which is exactly what we were expecting, which is a negative number, because if you look at the graph of the region, this entire region is below the x-axis. So this entire region here is below the x-axis, which is what we would expect. Now remember, definite integrals, which is what we're working with, give us net area, okay? And I'm reminding you of that because of this next example here. So with this next example, I want us to find the integral from -pi/4 to 7pi/4 of sine x plus cosine x dx. Okay? So I'm going to draw this for us. All right, so here is what this graph looks like. So there's -pi/4, 3pi/4, and 7pi/4. And that's what this graph looks like right here. Now, excuse me. Let me just label it real quick. So if you look at this, the area in the top and bottom, or better yet, the regions, region 1 and region 2, are equal to each other. They're the same. They're the same. Okay. So right now, if you're thinking about this without even knowing how to do this problem, the answer should be 0. Okay? If you wanted to be more precise, by all means, go ahead, use Desmos. All right? So sine x plus cosine x. Okay, and if you look, if you look at the area in the first region, in the second region, and in the third region, I mean, because this oscillates, you could see that they are the same, or at least visually, that's what they look like. To convince yourself that the answer to this problem is equal to 0, we have to know the integral of sine x, and we have to know the integral of cosine x. All right, and what's nice about this is they're just properties, they're rules. So the integral of sine x dx equals negative cosine x. I'm going to put a big box around it. That is unbelievably important that we know that. In fact, I'm going to upload this table of integrals, and you can use that for your test. Somebody went ahead and already figured out all these different types of integrals. So the first one, the integral of sine x dx equals negative cosine x. And the integral of cosine of x dx equals sine x. And there's your second property right there. So we're already starting to expand our rules for integrals. We have the power rule. Don't forget that power rule. The integral of x to the p dx equals x to the p plus 1 over p plus 1. All right. And if you wanted to, you could put that plus c here. I mean, technically you should. All right. But I'm just summarizing rules right now. So we got the power rule, and now you got two integrals, sine x dx and cosine x. All right. So let's go ahead. Let's figure out this problem. So our problem was the integral from negative pi over 4 to 7 pi over 4 of sine x plus cosine x dx. Okay, well, this one I'm going to go ahead and use some of the properties so you can see what's happening, but we're going to have to apply. We're going to have to apply the antiderivative for both of these. So we're going to get the integral of negative pi over 4 to 7 pi over 4 of sine x dx plus the integral of negative pi over 4 to 7 pi over 4 of cosine x dx. All right, so all I did was just I distributed my integral sign. Now we know from above the integral of sine x is going to be negative cosine x, and I have to evaluate this between negative pi over 4 and 7 pi over 4. Plus, I need to find the integral of cosine x. Well, from above, the integral of cosine x dx is going to be sine x. And I need to evaluate this between negative pi over 4 and 7 pi over 4. So this is kind of like two little mini problems in one. So we'll do the first one here. So I get negative cosine of 7 pi over 4 minus negative cosine of negative pi over 4. I'm going to put this in big brackets. Plus, now we're going to do the sine. The sine of 7 pi over 4 minus the sine of negative pi over 4. All right, and using our trusty unit circle, the negative cosine of 7 pi over 4, well, that's going to be negative square root of 2 over 2 minus, and then this is also going to be negative square root of 2 over 2 plus. Now the sine of 7 pi over 4, is negative square root of 2 over 2 minus the sine of negative pi over 4 is going to be negative square root of 2 over 2. And then as you can see here, I get 0 plus 0, which equals 0, which is exactly what we thought it should be given the rough sketch of the graph that we've created. Okay? Now remember, this is the definite integral, so this is the net area. If you wanted to find total area, you would have to break them apart. Okay? All right. So from here, what I'm going to do is just a bunch of examples. I'm not going to sketch as much anymore. I'm just going to go ahead and just knock out some examples for us.